Hello everybody, and welcome to the first video of Suspended Classes. In this video I just want to give a brief overview of Chapter 7. What is Chapter 7 about and what is it for? How does it fit into the structure of the course, and so on. Let me just say up front that with these videos I'm trying to keep them brief and to the point, as short as possible. This can be difficult for me. I tend to talk a lot when I'm talking about material I'm interested in, and I really like all the course material, but in particular, Chapter 7 is nice. So I am putting the restraints on to try to keep myself from just prattling on and on and on and on about this material that I like. So I apologize if I don't keep things as brief as possible. If you want me not to prattle on about things, if you want me to be brief, you should ask me about things like my taxes or about whatever stupid show my kids are into, like Paw Patrol or whatever. I have very little to say about those things. Okay, so the goal of this video is to discuss the parts of Chapter 7 that we will be covering while we are gone and talk about how Chapter 7 fits into the course itself. So Chapter 7 while we're gone. I'm assuming we'll be back on April 5th. If we are not back on April 5th, then of course things will change. But anyway, if you look at the schedule on Moodle, these were the sections that we were going to cover in the 2 weeks after spring break. So those are the sections that I'm hoping to cover now, this way. So I'm not planning on changing the material that we would have covered. The material itself will stay the same, although, as I've mentioned, I'm going to try to streamline it and the homework schedule will change, things like that. But the actual sections from the book will not change. Okay, so now what is Chapter 7 about? To answer that question, let's think back first to high school algebra. In a high school algebra class, like Algebra 1 or 2, you solved equations like 2x plus 7 equals 3, or any of these other three equations, right? You would have spent, months solving equations like this and just getting progressively more difficult. At some point, though, you started solving things like this. You started solving systems of equations, okay? And what does it mean to solve a system? Well, now you have sort of two equations and two unknowns. In contrast, of course, to these equations, you have one equation, one unknown. And this equation here has one equation, one unknown. In a system like this is a 2x2 system. You have two equations, two unknowns, and you have to solve the equations simultaneously. Solve them both at once. What does that mean? That means that your solution now consists not of just values for x, but values of x and y, so that when you substitute the x value back in for x and the y value back in for y, you get now two true statements, not just one true statement as you did with a regular equation like these guys. Okay, so in this case, the solution is x equals 14 and y equals 2. Why? Why is that the solution? Well, because if I put a 14 in for x and a 2 in for y, then this equation becomes a true statement, as does this one. Okay, so I'm not telling you anything new here, of course, right? But this is sort of the foundation that will motivate what we're doing in this chapter with differential equations. Okay, because Chapter 7 is about solving systems of not algebraic equations like these, but solving systems of differential equations. Okay, so solving multiple equations simultaneously at once, as you do here, back in Algebra 2. Okay, so let me just show you an example of such a thing. This is a system of differential equations. There are two differential equations here. And now there are actually two unknowns. The unknown functions are x1 and x2, and they are both functions of time, is the way this is set up, okay? So x1 is an unknown function of time. x2 is also an unknown function of time. This first equation is saying the derivative of x1 with respect to t, right? The derivative of x1 is x1 itself plus whatever x2 is. And this is saying the derivative of x2 is 4 times x1 plus x2. Okay? So the derivative of x2 is 4 times whatever x1 is plus x2 itself. This is a system of differential equations. What would it mean to solve this? It would mean to find all functions, x1 of t and x2 of t, such that when you put them both back into this system here, you get two true statements. So just for example here, consider these two functions. I'm not claiming it's clear where these came from. I'm just saying consider. So consider x1 of t equals e to the 3t plus e to the minus t, and x2 of t equals twice e to the 3t minus 2 e to the negative t. Well, notice a couple of things. Notice if I substitute x1 and x2 back into the first differential equation, I get this, okay? So what's the derivative of x1? Right, x1 is here. Its derivative is, by the chain rule, basically bring the 3 down, bring the negative 1 down, right? This is the derivative of x1. Okay, well, what is x1 plus x2? Here's x1, here's x2. When you add them together, you get this guy here. And notice, this blue highlighted right here equals this blue highlighted right there. So what do you know? The derivative of x1 is x1 plus x2, if these are the x1 and x2 you are talking about. And similarly, if you take the derivative of x2, right, x2 is here, you get this function here, bring the 3 down to get you a 6, bring the negative down to get you a plus 2, okay? Well, that's supposed to equal 4 times x1 plus x2. Here is 4 times x1 plus x2. And notice, again, this blue highlighted here equals this blue highlighted here, if you simplify. Okay, so this function, x1, combined with this function, x2, is a solution of the system. I put both them back into both equations, and I got something true. So now, instead of having a solution look like 14, comma 2, right? Number, comma, number. Now I have function, comma, function. That's a solution to this 2x2 system of differential equations. There were 2 equations and 2 unknowns. In Chapter 7, we'll focus on solving linear systems of DEs. That last example was an example of a linear system. A 2x2 system, so when I say 2x2, I just mean 2 equations, 2 unknowns, has this form. The derivative of x1 is this linear expression of x1 and x2, right? I just have addition and I have scalar multiplication. So you can imagine something like this example here. If instead of like 1 times x1, suppose I had t squared times x1. Or suppose I had x1 itself squared, or sine of x1, or whatever, right? Like, you can do whatever you want in general and you'll get a system. But to be linear means you're doing nothing wacky, and you're not really doing hardly anything at all. You're just scaling by constants and you're allowed to add. So this is what a 2x2 linear system looks like for us, okay? So after Chapter 7, we'll spend actually the rest of the semester analyzing nonlinear systems. So Chapter 7 talks about linear systems, and then past Chapter 7 we talk about nonlinear systems, and that's actually the entire semester. So all of the rest of the semester we are discussing systems of differential equations. These systems after Chapter 7, even though they are nonlinear, the linear systems we study here in Chapter 7 will be able to help us analyze the nonlinear system later in much the same way, right? In Calc 1, why do you study tangent lines so much? The reason is because the tangent lines, which are linear objects, right, can be used to understand all sorts of other graphs, because lines can give you nice little local approximations of any curve. Okay, so anyway, so that same kind of thing will happen here. Just like in Calc 1, you need to understand lines to understand other things. Here in this course, in Chapter 7, we'll have to understand these dudes to then understand the more complicated and more interesting systems after Chapter 7. Okay, why would you care about systems of differential equations? Is how we'll end this video. Why would you do this? Why would you consider this topic? Okay, well, the answer is because lots of things can be modeled by systems. And one context in which that arises is just when you have multiple populations floating around, each of which is a function of time. But you have multiple populations floating around, and their derivatives depend on the functions themselves. So, for example, in this system here, maybe x1 of t represents the number of people susceptible to a given disease. and X2 represents the number of people who are currently infected with it. Well, if this system indeed models the behavior of those two populations, then if you could solve this, you could make predictions about what happens. This number of susceptible people, does that go to 0 in the limit? This number of infected people, does like everybody get sick? Things like this, right? That's why you would care about systems of DEs. So after this chapter, we're going to be studying systems that model disease spread, epidemic models, and we'll be studying classical ecological models like predator-prey systems, things like that, competing species systems. Okay, so that's what Chapter 7 is about, and that's why we are studying it.